see how to find the best line for the linear regression model. Okay, so as I have already said, from this data, if we plot this graph, we will see that this blue line is the best line or the linear regression line. Okay, so now any like how we draw this line is basically from this data we actually calculate the intercept and the slope, which are the fixed parameters, and they will be, because for a particular line there will be a fixed parameters. Okay, they are to be determined from the data. Okay, so we determine them from the data. Now using that, when we have plotted that line or have drawn that line, we try to find out using that for 3,000 square feet, let's say the actual value is 578,000, and then so you will see that but the predicted value, which will be on the line, which is basically, let's say, y hat or y cap. So there is a difference between the actual value, which you find from the data itself, and the predicted value, which is here. So there is a difference. We call it a E1 or error 1. Okay, so it's a y hat minus y. So what is the difference? This difference is the difference between the predicted value and the actual value. And for all the points, every point, because a continuous line, so for all the points you can calculate the error E1, E2, E3 up to EI. And then what we do, what we say that what is the best line, how we find the best line is the line which you choose the line that minimizes the sum of the squares of the errors. Okay, all these errors I explained you minimize them this thing by adding the sum of the squares of the errors and then minimize the error. Okay, so this one more thing I want to tell you here, this equation, this predicted value y hat is mx plus b, or you can also written in other books and other places you will see it's written as more uniformly y hat equal to b0 plus b1x, where b0 is the intercept and b1 is the slope. Okay, and then there can be, if there's a multiple attributes or features are there, it can be b1, b2, b3 until so, but you have to calculate those intercept and slope from the data. Now you see there's a vector form of that same equation where you write the y hat equal to b as a vector and then x. Okay, x is also a vector here where x can be. So what is b then? First see, b is a parameter vector. Okay, so b0 and b1, that is the intercept and the slope for all the variables, also called the weight. Okay, so and for a generic case when there are multiple more variables or attributes, then we say it's a bi. For all bi you put them in the vector b, and all the variables the features you can put in the vector x. Okay, so what it will contain, all the values from x0 to xn. Like here x0 is the area, the value of an area, let's say 2,600 square feet. X1 can be the number of rooms, x2 can be the year built. So all this thing will be in the feature vector. Okay, so now this equation is kind of doing a dot product of it. Okay, so dot product we have already studied. So dot product is, let's say we are, write it in that way, y hat equal to b0, b1, b2, which is nothing but the vector b. This is the vector b, and this entire thing, and then this entire thing is the vector x. Okay, so this entire thing is the vector x, and then we are doing the dot product, and we are finding out that it's we have already studied dot product, so it's now a linear combination b0 times x0 plus b1 times x1 plus b2 times x2 in that way until bn times xn, considering there are n number of features. Okay, now coming back to the error, as I have already explained to you, the error is it's also called residual. Okay, sometimes error is called residual. So this is the difference between the predicted value and the actual value. Okay, so we want to minimize the sum of the squared errors. It's also called SSE. So we want to tell you that this concept comes from the RMSE, or the root mean square error, and minimizing the root mean square error and minimizing the sum of the squared error is basically the same thing. So we stick with it here because taking square root is another another step in the operation. We want to reduce that. So we want to minimize the sum of the squared errors subject to the constraint that the mean error is 0. That means the average error is 0. Okay, so I equal to 1 to n, EI equal to 0. So you have to calculate minimum of I equal to 1 to n sum of EI squared. That means all the errors, all the residuals, we take the square of them, sum them up, and then minimize that function, subject to the constraints, the optimization problem, that the mean error, the average error is 0. Okay, so this is nothing but saying that we want to minimize the variance of errors, and using that, if we can successfully do that, then we'll find that regression line, and then we'll calculate the intercept and the slope. Once we have found the intercept and the slope, then for any other value, we can predict the corresponding value for the whatever be the price of that house, or forecast stock prices, and similar kind of thing. Since the linear regression tries to reduce the sum of the square of the errors, this is also sometimes called the least square linear regression line.